It would begin to shed material during future spin increases. These shedding events, though subtle from a distance, could significantly alter the asteroid's evolution. When mass leaves the equator, the asteroid's moment of inertia changes, which in turn affects its spin. Depending on how much material is lost and how quickly, the asteroid might slow down, or it might spin even faster if the mass loss reduces its resistance to rotation. These complex interactions captivated mission planners, who saw the asteroid as a perfect test case for future robotic exploration. The idea of landing a spacecraft on such a dynamic, rapidly rotating surface posed tremendous challenges but promised even greater rewards. Engineers debated designs for a lander capable of anchoring itself securely, resisting sliding forces, and operating on terrain that could shift beneath it. Some envisioned a claw-like anchoring system capable of drilling deep into the surface. Others proposed a lander with multiple microthrusters designed to stabilize itself against centrifugal drift. A few researchers explored the idea of using harpoons or penetrating anchors to latch on a solid rock beneath the loose regolith. Each design had advantages and drawbacks, but all shared one common difficulty: the asteroid's rotation. At its current rate, the asteroid completed one rotation in a fraction of the time typical for medium-sized asteroids. This rapid spin meant that any lander would experience a constant sideways pull, as if standing on the side of a rapidly spinning carnival ride. Traditional landing strategies would be ineffective. A spacecraft might need to match the asteroid's rotation before touchdown, requiring complex maneuvering and precise timing. These engineering challenges did not deter mission planners. Instead, they fueled new innovation. Some teams proposed sending a fleet of tiny hopper bots, agile robotic explorers capable of bouncing and gripping terrain. Others suggested deploying a hovering drone-like craft that would map the equatorial ridge from just meters above the surface, avoiding the need for landing altogether. As the debate continued, space agencies began discussing international cooperation. The asteroid had become important enough to warrant a joint mission, similar to the way multiple nations collaborated on exploring comets and distant worlds. Such collaboration would allow scientists to share expertise, distribute costs, and assemble a mission capable of conducting cutting-edge science. At the same time, the accelerating asteroid began attracting public attention. Popular science documentaries featured its rapidly changing surface. Educational videos used it to explain the YORP effect. Space enthusiasts followed its measurements year by year, tracking how its spin changed over time. The asteroid became a symbol of how dynamic and alive the solar system truly is. Even artists, filmmakers, and storytellers began incorporating it into science fiction. Some imagined a future where humanity constructs artificial habitats on such fast-spinning objects, using their rotational speed to generate centrifugal gravity. Others wove narratives about mining missions gone wrong or alien civilizations using asteroid spin manipulation as a means of propulsion. Yet, despite all the attention and speculation, the asteroid continued its journey unchanged. While humans debated, modeled, imagined, and planned, the asteroid spun on, indifferent to the fascination it inspired. Its evolution was guided not by strategies or committees, but by sunlight, dust, rock, and time, forces that had shaped it long before humanity existed. As observations continued, scientists discovered that the asteroid's acceleration was entering a new phase. For years, its increase in rotation had been steady and predictable, but now the curve was bending upward. The speed increase was becoming nonlinear. This raised new questions. Was the asteroid undergoing a structural shift that was amplifying the YORP effect? Had a recent shedding event exposed fresh dark material? Or had the changing orientation of its orbit altered the angle at which sunlight struck it? The data showed that something had changed, but what? Instruments detected subtle differences in the asteroid's brightness, indicating that new material had been uncovered. Radar scans confirmed slight alterations in the shape of the equatorial bulge. Thermal readings showed hotspots forming where colder regions had existed before. These variations were unmistakable signs of surface transformation. A significant slumping event had likely occurred, an avalanche of dust sliding down the steep equatorial ridge, exposing new layers of rock beneath. This newly exposed material, darker and more heat-absorbent than the surface dust, amplified the YORP effect, causing an even faster increase in rotation. This was the moment scientists had been waiting for, direct evidence that surface changes could influence the asteroid's spin significantly. The asteroid was confirming the very models that had predicted such a feedback loop. It was a living demonstration of cosmic evolution on a scale humanity could witness. And as the asteroid entered this new phase of acceleration, researchers prepared for even more dramatic changes in the years ahead. With each rotation, the asteroid became more dynamic, more complex, more alive in its silent cosmic ballet. Scientists observed that surface material continued to migrate toward the equator, reinforcing the ridge and gradually reshaping the asteroid's overall geometry. This process, seemingly slow and insignificant on a human scale, was monumental in terms of planetary physics. Over decades, centuries, and millennia, it was altering the asteroid's structural integrity, preparing it for eventual shedding events or total breakup. The asteroid's internal stresses were also evolving. As rotational speed increased, centrifugal forces began pulling at internal fractures that had existed for billions of years. These fractures, invisible from the outside, acted as weak points within the asteroid's core. Simulations suggested that over time, the stress would reach a threshold where even minor vibrations or impacts could trigger microfractures, causing sections of the interior to collapse inward. This, in turn, could redistribute mass and further amplify rotational acceleration, creating a self-reinforcing cycle. In a way, the asteroid was approaching a tipping point, a critical state at which its structure could no longer resist the forces acting upon it. Yet, despite this looming instability, the asteroid exhibited remarkable resilience. Its internal cohesion, while imperfect, allowed it to endure increasingly rapid rotation without immediate catastrophic failure. This balance between fragility and stability captivated researchers. It was a lesson in the delicate equilibrium that governs small bodies in the solar system. Meanwhile, robotic missions and planning stages began to incorporate this new understanding into their designs. Engineers realized that any lander or sampling mission would need to account not only for the asteroid's rapid spin, but also for potential surface instability. Anchoring mechanisms, mobility systems, and sampling equipment would all have to operate in an environment where material could shift unexpectedly and centrifugal forces could push objects outward. The challenges were immense, but the potential scientific payoff was unprecedented. Astronomers continued to refine their models, incorporating observational data from optical, radar, and thermal instruments. They adjusted their predictions for rotational acceleration, surface migration, and structural stress. Each refinement brought new insights and raised new questions. Could the asteroid reach a stable rotation before catastrophic breakup? Would mass shedding events occur gradually or abruptly? Could external factors, such as small impacts or gravitational interactions with other celestial bodies, trigger sudden changes? These questions underscored the complexity of asteroid evolution. Unlike planets or moons, which benefit from substantial gravity and internal cohesion, small bodies exist on the edge of structural stability. Tiny forces, solar radiation, thermal effects, minor collisions, can produce dramatic consequences over long timescales. The asteroid spinning faster every year exemplified this principle in its purest form. Observational campaigns intensified. Ground-based telescopes monitored subtle changes in brightness, tracking how the asteroid's rotation affected its light curve. Radar facilities mapped the surface and interior in increasing detail, revealing variations in topography, ridge formation, and potential voids. Infrared instruments measured thermal anomalies, indicating regions of exposed material and active surface evolution. Every piece of data contributed to a growing understanding of the asteroid's behavior, providing a rare opportunity to witness real-time cosmic processes. The scientific significance extended beyond a single asteroid. By studying fast-spinning objects, researchers gained insights applicable to the broader population of small solar system bodies. Many near-Earth objects share similar characteristics: irregular shapes, rapid rotation, and surfaces shaped by centuries of exposure to sunlight and micro-impacts. Understanding how rotation, mass redistribution, and thermal forces interact in one asteroid provides a template for predicting the behavior of countless others, including those that might pose potential threats to Earth in the distant future. The philosophical implications were equally profound. Here was a small, seemingly insignificant object, orbiting silently through the vast emptiness of space, yet responding to forces so subtle they are nearly invisible. Light, the most gentle and pervasive force in the solar system, was sculpting its destiny. Over millions of years, photons had nudged it from one state to another, gradually accelerating its rotation and reshaping its form. The asteroid story was a testament to the power of patience, persistence, and infinitesimal forces, illustrating that even in the universe's vastness, small changes can have monumental consequences. As this understanding spread through the scientific community, global collaboration intensified. Observatories, universities, and space agencies coordinated monitoring programs, shared data, and refined predictive models. The asteroid became a unifying subject of study, bringing together experts in physics, engineering, planetary science, and astronomy. Each observation, each simulation, each theoretical insight contributed to a more complete picture of its evolution and potential fate. Public engagement also grew. Documentaries, articles, and educational programs highlighted the asteroid's unique characteristics and the scientific lessons it offered. Amateur astronomers tracked its movement, adding observations to professional datasets. The asteroid, once anonymous, became a symbol of human curiosity and the desire to understand the universe. Its gradual acceleration and visible evolution captured the imagination of people around the world, connecting them to a cosmic process unfolding over timescales far longer than a human lifetime. Yet, for all the observation, calculation, and fascination, the asteroid itself remained indifferent. It rotated year after year, accelerated by forces indifferent to human scrutiny. Its mass migrated, its surface shifted, its spin increased, yet continued its silent journey through the void, guided by the immutable laws of physics. In this sense, the asteroid was both a teacher and a reminder. The universe operates on scales, forces, and rhythms that often transcend human perception, yet it leaves traces for those who look carefully enough. As the asteroid approached a point where centrifugal forces could overcome the structural integrity of its outer layers, scientists began to anticipate the first signs of active mass shedding. Small particles might lift off the surface, drifting into space, forming a transient halo around the asteroid. Larger boulders could detach, creating temporary satellites or even sparking binary formation. Such events, while subtle in the immediate term, had profound implications for understanding rotational breakup and the life cycle of small solar system bodies. The prospect of these events encouraged a new generation of mission concepts. Space agencies explored technologies capable of in-situ monitoring, including orbiters, landers, and sample return systems designed to operate in highly dynamic, low-gravity environments. Advanced sensors would capture the movement of surface material, monitor rotational acceleration, and measure changes in internal structure. Every insight gained from such missions would not only illuminate this asteroid's evolution, but also inform planetary defense strategies, resource utilization, and future exploration of small bodies throughout the solar system. Ultimately, the story of the asteroid that spins faster every year was a story about time, patience, and subtle forces. It demonstrated that the universe is alive with processes that are often invisible, yet powerful. It illustrated how sunlight, thermal variation, and material redistribution, forces so delicate that they could be dismissed as negligible, could shape worlds over millions of years. And it underscored a profound truth. In the cosmos, even the smallest objects are subject to forces that sculpt, evolve, and, eventually, transform them entirely. Through continuous observation, simulation, and planning, humanity has learned to witness this process with unprecedented clarity. We watch, we measure, we model, and we prepare. And in doing so, we connect not only to this spinning rock in the void, but to the broader rhythms of the universe, reminding us that time, forces, and evolution operate on scales that dwarf our daily lives, yet ultimately govern the destiny of all things. The asteroid continues to spin faster every year, slowly, relentlessly, and with a quiet inevitability. Its future is not yet written in stone. Its evolution remains a complex interplay of light, material, rotation, and time. But its path is clear. The forces acting upon it will continue to shape it, as they have for billions of years, until it either stabilizes, sheds mass, or undergoes complete rotational breakup, scattering its material across the void as both witness and testament to the subtle power of the cosmos. As the asteroid continues its journey through the void, spinning faster with each passing year, scientists maintain a vigilant watch. Observatories, orbiters, radar systems, and thermal imaging instruments form an invisible web of monitoring across the globe. Each photon of light reflected from its surface, each faint shift in dust patterns, each minute variation in brightness contributes to a growing understanding of its dynamics. Humanity observes a celestial phenomenon that has existed for billions of years, now unfolding within the scope of human perception, a rare convergence of cosmic timescales and technological capability. The accelerating rotation has begun to exert profound influence over the asteroid's surface and internal structure. The equatorial ridge, once subtle, has grown more pronounced, a silent monument to centrifugal forces at work. Dust slides down its slopes, boulders migrate outward, and fine particles escape entirely, drifting into space. Observers witness the subtle beginnings of mass shedding, a prelude to more dramatic evolutionary events. Each small movement reinforces the delicate balance that governs its stability, while also providing a live demonstration of rotational mechanics in action. Simulations suggest that the asteroid will eventually reach a critical rotational threshold. At this point, the combined forces of gravity, cohesion, and centrifugal acceleration will be unable to maintain structural integrity. The asteroid may fragment into multiple pieces, some remaining gravitationally bound as a binary system, others sent spinning into independent orbits. Yet whether this occurs abruptly or through a series of smaller shedding events, the asteroid will continue to evolve, responding to the same physical laws that have governed it since the formation of the solar system. This cosmic process is not destructive in the sense humans often imagine. It is elegant, deliberate, and a natural aspect of small body evolution. The asteroid's rotation, driven by the gentle push of sunlight over millions of years, demonstrates the profound influence of forces that are almost imperceptible yet capable of reshaping worlds. In this, the asteroid serves as both teacher and example, a reminder that even the smallest influences, applied consistently over time, can lead to dramatic change. Scientists continue to model future outcomes. The asteroid may reach a new equilibrium after shedding mass, stabilizing at a slower rotational rate. Alternatively, it may spin beyond its breaking point, fragmenting into multiple pieces and creating a miniature debris system that traces new orbital paths through the solar system. Observers study each possibility, refining predictions and preparing for potential impacts on orbital mechanics in the broader asteroid belt or near-Earth space. The implications extend beyond a single object. They inform planetary defense strategies, resource exploration, and our understanding of cosmic evolution. Yet the narrative of this asteroid is as philosophical as it is scientific. It illustrates a fundamental truth. The universe evolves not only through violent collisions or catastrophic events, but also through subtle, persistent forces acting over long durations. Sunlight, a force so seemingly trivial, can drive the transformation of a small body across eons. Rotation, mass redistribution, and thermal effects conspire to shape the destiny of worlds. And in witnessing this process, humanity gains a profound perspective on time, change, and the fragile balance of forces that govern existence. For centuries, the asteroid has orbited silently, indifferent to observers, untouched by civilization, unshaped by human hands. Today, it is the focus of meticulous study, a bridge between deep cosmic timescales and human curiosity. It represents the continuity of natural processes, a stone born from chaos, sculpted by forces both subtle and immense, evolving steadily in the vastness of space. Observing it teaches patience, precision, and humility, an understanding that even the most incremental forces, given enough time, can produce monumental outcomes. As the asteroid spins faster every year, its future is both inevitable and unknowable. Centrifugal forces will continue to shape its surface. Material will migrate, cracks will form, and eventually, its structure may fail, resulting in the dispersal of fragments across the void. Yet this is not an end. It is a continuation of cosmic evolution. Pieces of rock will drift into new orbits, some potentially seeding new systems, others colliding with other celestial bodies, contributing to the ongoing cycle of creation and transformation that defines the solar system. In the quiet darkness of space, this small asteroid tells a story that spans billions of years. It is a story of light and shadow, of rotation and force, of evolution both subtle and profound. Its motion serves as a living record of processes that have shaped the solar system since its earliest moments. And as scientists continue to measure, observe, and model its changes, humanity participates in a rare privilege: the ability to witness real-time cosmic evolution, to understand the mechanics of a spinning world, and to reflect on the delicate balance that governs all celestial bodies. The asteroid spins faster every year, silently, gracefully, inexorably. It reminds us that even the smallest, most unassuming objects in space are subject to forces capable of transformation, fragmentation, and renewal. Its journey teaches us that evolution need not be loud or violent. It can be patient, incremental, and persistent. And in that truth lies the beauty of the cosmos, a system governed by subtle forces, ancient processes, and the persistent passage of time. Ultimately, this asteroid is not merely a rock. It is a living lesson in physics, a monument to the quiet power of light, a witness to the slow but inevitable transformation of worlds. It is both ordinary and extraordinary, mundane and miraculous, a spinning sentinel in the solar system, teaching all who observe it that time, force, and motion are the architects of the universe. And as it continues to spin faster every year, it leaves humanity with a profound understanding that even in the silent vacuum of space, evolution never stops, and every object, no matter how small, has a story worth observing, a lesson worth learning, and a destiny shaped by the delicate yet relentless forces of nature.